Now that we've looked at orbitals and electrons, and we've started to fill orbitals with electrons, we're going to examine the periodic table and the periodic nature of elements based on electrons. Now, by the mid to late 19th century, many elements had been discovered, and it became evident that there was a method needed to organize these elements. Several scientists began to recognize patterns among elements and tried arranging elements by different methods, such as groups of threes or triads or octets, groups of 8. None of these methods of organization really worked out very well. The present form of the periodic table was proposed by Meyer and Mendeleev, although Mendeleev is given most of the credit for the current version because he truly emphasized how useful the periodic table could be in predicting the existence and properties of unknown elements. He was able to predict the existence and properties of elements that had not been discovered yet and stated where they should be on the periodic table. He was also able to correct some masses for elements that were already known. The modern table, which can be seen on the inside cover of your textbook, is arranged by atomic number. This is an excerpt which shows an early version of the periodic table developed by Mendeleev. Now, as protons are added one by one to the nucleus to build up elements, electrons are similarly added. We add these electrons to hydrogen-like orbitals, and they fill successively higher energy orbitals as we begin to place electrons into orbitals. So with hydrogen, we only have one electron in the 1s orbital. With helium, we place a second electron in that 1s orbital, so we have an electron configuration of 1s2. Now remember, by the Pauli exclusion principle, these two electrons must have opposite spin to be in the same orbital. When we get to the next element, lithium, we begin to put electrons into the second period, as is indicated by the number 2 as a primary quantum number. All elements in the second period have electrons going into a orbital in the second quantum level. So as we fill from lithium to beryllium, we do exactly what we did with hydrogen and helium. We put an electron into our 2s orbital and then another electron into our 2s orbital. When we go across the periodic table to the fifth element, boron, we use a new type of orbital, a p orbital. So boron has one electron in its p orbital. We begin filling our 2p orbitals until we get to neon, where we end up with a filled subshell. That filled subshell is important to recognize. Our total number of electrons in the second period is 8, which is an octet of electrons. We're going to see that when we reach that octet of electrons, we have a particularly stable electron configuration, and our element becomes very non-reactive. As we drop down to the next set of elements, we go to the third period and begin filling the third principal quantum level as we go across to argon. Now it's important to recognize that elements in the same vertical column or group of the periodic table have the same valence shell electron configuration. Valence shell electrons are the electrons in the outermost principal quantum level. These are the electrons involved in chemistry and bonding. These are the key electrons that we're going to want to focus our attention on. The electrons that are not in the outermost shell are called core shell electrons or inner shell electrons. These electrons are not available for chemistry or bonding. Now, one thing to remember as we put electrons into orbitals is that the lowest energy configuration for an atom is the one having the maximum number of unpaired electrons allowed by the Pauli exclusion principle in a particular set of degenerate orbitals. Degenerate meaning same energy orbitals. So if we take a look at oxygen's electron configuration, we have 1s2, 2s2, 2p4. If we rewrite that in an orbital box diagram where we show how many electrons an atom has in each of its occupied electron orbitals, we see 2 electrons in our 1s orbital of opposite spin, 2 electrons in our 2s orbital of opposite spin. Then when we get to the set of 2p degenerate orbitals, we see in our 2px orbital a pair of electrons of opposite spin. In our py and our pz, we have single unpaired electrons because by Hund's rule, that is the lowest energy conformation for oxygen. Instead of having 2 sets of paired electrons in our 2p orbital, we have 1 set of paired electrons and then 2 single unpaired electrons. Now again, we're going to want to focus our attention on our valence electrons, which are the electrons in the outermost principal quantum level of an atom. If we look at the element neon with the elemental symbol Ne, we have an electron configuration of 1s2, 2s2, 2p6. The number of valence electrons, the electrons in our outermost principal quantum level, is 8. 6 plus 2 in the second principal quantum level equals 8. In many cases, it's much more simple to represent the core shell electrons using the notation of the previous noble gas. In this case, helium would have the 1s2 core shell electron configuration, so we write the elemental symbol for helium and then only list the valence shell electrons for neon, 2s2, 2p6. Again, keep in mind that elements in the same group, in the same vertical column of the periodic table, will have the same number of valence electrons. The only difference will be the principal quantum level that those electrons are placed in. So if we look at the entire periodic table, all group 1a elements have a single electron in their outermost s orbital. All group 2a elements have a single electron in their outermost, have 2 electrons in their outermost s orbital. Now let's jump across the transition metals to the other representative or main group elements. Group 3a has 3 valence electrons in its principal quantum level. Group 4a has 4 electrons in its principal quantum level. Group 5a has 5 valence electrons in its principal outermost quantum level, and so on and so forth until we reach the noble gases. Those elements are referred to as main group elements, where we're filling s and p orbitals as our valence shell. The similarity among the transition metals is that they all have electrons in d orbitals. The lanthanide and actinide series have electrons in f orbitals. In most cases, as we go across period 4, from potassium, element number 19, to krypton, element number 36, we fill electrons into our orbitals as the energy increases successively. There are a few notable exceptions to this. At element number 24, chromium, and at element number 29, copper, we see a slight anomaly. As we go across that 4th period, In the D block, we see that going from vanadium to chromium, we go from 4s2 3d3 to 4s1 3d5. We put one of our s orbital electrons into the d orbital and then also add another electron into the d orbital. That gives us 6 unpaired electrons. It is more stable to have 6 unpaired electrons with a half-filled d shell than it is to have the paired electrons, because a d orbital is very close in energy to an s orbital. Again, when we get to copper, we see 4s1 3d10. It's energetically more favorable to have a filled d shell than it is to have a pair of electrons in the 4s subshell. So now, if we look at the periodic table, we can see which orbitals are being filled in which parts. In the main group elements on the far left, we're filling s orbitals. These are the s block elements. On the far right, for main group elements, we're filling p orbitals. In the center, for the transition metals, we fill d orbitals. The lanthanide and actinide series, which is separated out, we fill f orbitals.